Alright, here we are. So welcome back. We are in the middle of the proof of the real Hahn-Banach theorem, which is an extension theorem for linear functionals on real vector spaces. We did some work in the last video that was dealing with extending sort of the functional that is given to you to, well, a vector space that is sort of one vector bigger. And now the idea is, once we know how to do this once, then we will do it arbitrarily often by using Zorn's lemma. So that's why I thought I quickly go back to this slide here. So remember, Zorn's lemma, we used it before in the proof of existence for orthonormal basis. So it has to do with something, you know, completely non-functional analytic, namely relations. So here, just to recap, relation is a subset of a Cartesian product. And there's four properties that usually float around: reflexive, symmetric, transitive relations. But for the Zorn lemma, actually, you need the anti-symmetric relation. All right. Then there's the notion of partial order. So partial order is a relation that is reflexive, anti-symmetric, and transitive, and it gets a special symbol. Almost looks like this less than or equal sign, but sort of bended a little bit. And if a set is equipped with a partial order, a distinguished partial order, we say it's a partially ordered set. Prototypical example is the real line. That is a partially ordered set with the ordinary inequality. Sets can be partially ordered, or say the power set of a set can be partially ordered by set inclusion. However, one has to be careful, because two elements in a partially ordered set might not be related to one another, and that is precisely what the total order achieves, right? So in a partially ordered set, is totally ordered if either x is related to y or the other way around, right? This might not be the case for your sets, because you know you have two sets A and B. They might be disjoint, so you can't assume that one is always sitting in the other. A totally ordered subset is called a chain. Now, upper bounds, well, this is very much, I had this example, you take an interval 0 to 1, then an upper bound would be, for instance, 2. So that is true, and then the maximal element. Once you have these notions on the table, then here comes Zorn's lemma. So if you have a non-empty partially ordered set, in which every totally ordered subset, aka a chain, has an upper bound, then that whole set X has at least one maximal element. And that's what we're going to use now in the proof of the Hahn-Banach theorem. So let's go back here. So we need to define, well, the appropriate set X. We need to introduce a partial order on it, pick an arbitrary chain, show it has an upper bound. Then Zorn kicks in, guarantees existence of a maximal element, and then we have to convince ourselves that that maximal element is what we need for the statement of Zorn's theorem. Okay, good. So here's the set. So let curly P be pairs y0, f0. So this is going to be slightly more abstract than the proof of the theorem there in the Hilbert space chapter about existence of orthonormal basis, because there was just that set C was collection of orthonormal sets, but here it's pairs. So what kind of pairs am I looking at? So denote the set of all pairs. Well, why not? So that y is properly contained in y0, and this is a subset of X. This is what we achieved in this extension proposition right above this proof now. And then, of course, the f0 would be the linear functional that has these good properties on y0. And linear functionals, y0, oh no, f0, sorry, f0 from y0, real valued, obeying f0 z less than or equal p of z for all z in y0, and, well, the reproducing character f0 of y is equal to f of y for all y in y. Okay. Note by the previous proposition that set up here that curly P is non-empty. All right. As soon as this Y here is a proper subspace of X, the previous proposition guarantees that P is a non-empty set. So this is sort of step 0 in the application of Zorn's lemma. You have to make sure that that set that you're working with is non-empty. Okay, here it is. Now step 1 is introduce the partial order on it. Okay. Maybe let me write this down that the set is non-empty. I see I have written it in my notes. This set is non-empty by the last proposition. Okay. Now the partial order. Next, P is partially ordered by what I will call extension. What does that mean? Well, so we say, well, now we have these two pairs, right? So we have y1 and f1, and they are related to y2, f2. This is by definition now if and only if, well, y1 is a subset of y2. That makes sense because you wanna extend your subspaces sort of in some fashion. So one should be contained in the other, and the one on the bigger one on y2, well, it reproduces the one on the smaller one once you are in the smaller one. So f2y is equal to f1y when y is in y1. Okay, now you have to check that this is indeed a partial order, that is to say it's reflexive, transitive, and anti-symmetric, but that is easy to see. Okay. All right, moving ahead. Now we have to pick an arbitrary chain that is a totally ordered subset of curly P. Right, so moving ahead. Pick any chain. Well, let's give it some index. Y alpha, F alpha. Alpha index set can be uncountable in P. It has any totally ordered subset of P. Now I have to construct an upper bound. And that step is kind of, similar to what we did in the proof of that basis theorem in the Hilbert space world. There we looked at the union of all the orthonormal sets in that chain, and that's kind of what we do here. Then, so first look at the union of all those y alphas, but now you also have to introduce a functional, right? Because we are looking here at pairs, not just subspaces. Well, that functional f star will just be equal to, well, the restriction f alpha y when y is in y alpha, right? And this is well defined because if you take an element here in this union, then it is in at least one of the y alpha. That's what, after all, the set union means. And then you can make sense of f star y on all of the union, right, in the way it is indicated. All right, so this makes sense. Okay, so now we have to check a few properties. Claim is an upper bound. That's what I want, after all. Is an upper bound for the chosen chain. Why? Well, first, is this a subspace? Yeah, that's a subspace. So this is a fact in linear algebra already. It has nothing to do with the dimension. If you take unions of subspaces, countable or uncountable, they're always subspaces. That's because of the set union character. So Y is a subspace of X for if, well, I have to show that it's closed under the typical vector space operation. So if this is in here, 2 points, x, y, then here subspace, x, y is in a y beta in X for at least one beta, for some beta in the index set. And since this is a subspace, the y beta, each one of those guys is a subspace, so that means the linear combination, all linear combinations that you can form out of those two vectors, so the span of x and y is then again in y beta. Yeah, but y beta, of course, is sitting in the union of all these guys, right? So that's why it's a subspace. That's clear. Second, is this f star a linear functional? Well, yes, it is, but because it's just defined as the restriction to all those f alphas, and those guys are linear functionals, right? Second, f star is clearly a linear functional. Okay, with the desired properties by construction. Okay, so together that element that I constructed up there, that union of the y alphas and the f star, is certainly an element in P. Okay, this is the first thing that you have to check when you claim something is an upper bound, right? That it is in the big partially ordered set that is here P. Okay, and I have to check the second criteria, which is really what it means, the upper for something to be an upper bound. Every chain, so moreover, every y gamma f gamma in the chain satisfies, well, it should be less than or equal to, but less than or equal, meaning this order relation, satisfies y gamma f gamma like this, alpha in I, y alpha, f star y. Okay, maybe here I shouldn't write the argument, just f star, to be consistent in my notation, and maybe up here the same, just f star, because I'm not evaluating on a point here anymore, like this. Okay, and this is true again by construction. Right, because certainly this arbitrary y gamma is a subset of the union of all the y alphas, and if you take the big guy and you restrict it to the small one y gamma, then by definition it precisely reproduces, it's written up there, the f gamma, right? So that's clear. All right, good. So that means this guy really is a upper bound, and so hence Bizorn's lemma, there exists a maximal element of P, right? There exists a maximal element of P, say y infinity f infinity. Okay, now we will have to show that this maximal element, well, it does what we want from it, that is to say that y infinity should be the whole space, right? So y infinity should be in particular equal to x. So if not, if y is still proper subspace in X, by the previous proposition, you can extend it again. By previous proposition, we can find vector x in the complement of y infinity and a linear functional, say G0 on Well, y infinity 0, that is just y infinity extended by this one vector, so alpha x, just as we had it before. Okay, so that g0 of y, well, reproduces f infinity on y infinity. Yeah, that's it. That's all that I need, right? In turn, I don't need the inequality right now. I just need this, right? So in turn, y infinity, f infinity would not be maximal. Since, well, simply y infinity 0 is not equal to y infinity, right? Because the definition of a maximal element guarantees that these two guys have to be the same, but here they are not, so our assumption was wrong. Okay, good. So we conclude that y infinity is equal to x, and now how do we find our extension? Well, that capital F that is claimed to exist in the Hahn-Banach theorem, this precisely f infinity. It reproduces the small f when you restrict yourself back to the proper subspace y. This is by construction, just read the proof backwards, and it satisfies the inequality. F of x less than or equal to, this is a p of x for all x in x, and what I said earlier, when you restrict yourself, it reproduces the small f when y is in y. Okay, this completes the proof of the theorem. Okay, all right. Right, so this is a long way. It's, I would say this much. I mean, most of the theorems here in functional analysis, with a little bit experience, you can prove from scratch by first principles. But the cases where you have to invoke Zorn's lemma, those are of a different technical nature, right? Because I mean, it's not so clear up front how you want to define the partial order on your set, and so that is a trial and error process. It's not, I wouldn't be able to give you a recipe that will always work. It's trial and error, and this recipe works. Okay, so this is Zorn's lemma. It is unfortunately a non-constructive proof. One can again make things somewhat more constructive, maybe not so surprising if your vector space is separable. This is just as it was in the Hilbert space case. When you have separable Hilbert spaces, then you know the existence of those linearly independent spanning sets, and they follow by induction, and then you orthonormalize them and by Gram-Schmidt, and then you're done. Similar thing can be done here if you're in a separable space and also a separable normed linear space. Then you can use ordinary induction, doing this proposition and then extending one dimension at a time, essentially. Okay, but here I proved it in full generality. Okay, good. So this is the real Hahn-Banach. Now we first prove the complex Hahn-Banach, and then we will see what this theorem does for us and why it is so important. Okay, so next definition to go to the complex vector space world. So let X be a complex vector space. Again, this just means that the underlying scalar field is the complex number field. A function P from X, real valued, is called symmetric if for all x in x, complex lambda on the boundary of the unit disk, we have p lambda x is equal to p of x. Okay, so in a sense, those are symmetric functions. Those are the ones invariant under, well, rotation of the vectors, right? Because these complex numbers on the unit, on the boundary of the unit disk, these are of the form e to the I theta, theta some angle, and that corresponds to a rotation, right? So symmetric functions are those invariant under rotations. In particular, the norm is a normed linear vector space is a symmetric function, right? Because if you pull out the scalar, it comes out with complex modulus of it, and since that is equal to 1, the norm is invariant. All right, so now here comes the complex Hahn-Banach theorem. Complex Hahn-Banach. Okay, so we will have time to state the theorem, probably not to prove it, but that's okay. We'll do it in the next video. Let X be a complex vector space, P a symmetric convex function, Y in X a complex subspace, and F YC a linear functional obeying, well, f of y, of course I can't compare to a real number because it's in general complex, but the modulus I can, so that's what's now bounded by that convex symmetric function for all y and y. Okay, so these are the ingredients: complex vector space, symmetric convex function, complex subspace, and linear functional obeying, you know, this inequality there. So the complex modulus is dominated by the symmetric convex function. All right, and then the punchline, well, very much like earlier, then there exists a linear functional capital F on the whole space, complex valued, satisfying f of x less than or equal to p of x on all of x, so for all x in x, and it again reproduces the guy you started with, so small f of y for all y and y. Okay, that's the statement. As I said, punchline exactly the same as in the real Hahn-Banach. Existence of extension that is dominated in complex modulus by the given symmetric convex function, and the extension is really an extension in the sense that it reproduces the small f once you're again back to your initial subspace. Okay, that's the statement. The proof of the complex Hahn-Banach theorem is much easier than the one for the real Hahn-Banach, but that's maybe not so surprising because we will play around with real and imaginary parts of our functionals, and for those we have already done the hard work. That is to say, we have proven the real Hahn-Banach theorem. Okay, so I will do this in the next video, and then there will be, let's count here, 1, 2, 3, 4, 5, 6. There will be 6 important consequences, 6 corollaries that we will discuss, prove, and then apply. Okay, yeah, that's the plan then for the next video, or maybe even the next 2 videos. All right, see you then.